Now that you've seen some different types of equilibrium expressions for acids and bases, and also for seemingly insoluble things that are partially soluble, let's talk about complex ions, which is module 5.2.2.3. Okay, and so we talked about complex ions a little bit earlier. Okay, these are things that have a central atom or ion, which is usually a transition metal, and they're surrounded on the outside by ligands, which might be ions or small neutral molecules like maybe water or ammonia. Okay, and so let me show you how these might form, and then we'll show you the kind of mathematical description or explanation of the kind of equilibrium for these processes. Okay, and so let me show you a relatively simple experiment first. Let's pretend that you had a solution of silver chloride, okay, AgCl. So you saw this earlier, hopefully in the last video, that AgCl is one of these insoluble salts that only dissociates to a very, very small extent. Okay, and so that means that typically if you had a solution of AgCl, it would be almost entirely solid AgCl and only a very, very small amount of Ag plus and Cl minus. Okay, and let me write down the equilibrium for you over here. Okay, and so AgCl, solid, is going to dissociate into Ag plus and Cl minus. Now, that would be true if it was just water. Okay, I would have a small amount of silver ions and a small amount of chloride ions. But now let's say that I actually change the conditions of the experiment, where instead of dissolving the AgCl in just pure water, I actually try to dissolve the AgCl in salt water. Okay, I add NaCl, right, sodium chloride, to the water. Okay, and so what's going to happen? Well, the NaCl is a pretty good electrolyte, dissociates completely, and breaks apart irreversibly into sodium ions and chloride ions. And the point is that the NaCl is going to be a source of extra chloride ions. And so if I'm increasing the concentration of chloride ions, I can think of this in terms of the Chatelier's principle or something called the common ion effect. Since I have more Cl minus around, the equilibrium should shift to the left. And so the solubility of AgCl should actually decrease as the concentration of Cl minus increases. Okay, and if you look at the table, you'll see that behavior. Okay, as I increase the concentration of of chloride ion, the predicted solubility goes down and down and down, right? These get smaller and smaller and smaller and smaller. And if I actually do the experiment and make the measurements, you see that it does start to decrease, but then something weird happens around here, and the solubility actually goes up again, and it actually increases to the point where it's more soluble at these very high salt concentrations than it was before. And you say, whoa, that's weird. What the heck's going on? Well, there's another chemical reaction taking place. So let me show you what that is. Okay, we're forming complex ions. Okay, and so what can happen is at super high concentrations, the silver ions can react with maybe N of these chloride ions and form some kind of equilibrium to have AgClN. And then the whole thing has a certain charge associated with it. Okay, so for example, maybe I have 4 chloride ions, so it might form AgCl4 with a charge of -3, just as an example. Okay, these complex ions are really polyatomic ions. So there's a cation or an anion that consists of some kind of central atom, okay, which is going to be in this case the silver ion or Lewis acid, electron acceptor, and these ligands, which are on the outside, okay, that are bonded to it via coordinate covalent bonds. And so in this case, the chloride ions are the ligands. And the point is that there's going to be a certain equilibrium constant for these reactions. And we're going to call these equilibrium constants Kf. Okay, the F stands for formation. And you can see in this table that in contrast to the KSPs, which were super, super small, a lot of these KFs are actually super, super big, which means that the equilibrium heavily favors the products compared to the reactants. Okay, so these reactions actually happen quite easily, especially if you have very, very, very high concentrations of the ligands present, kind of drive the equilibrium to the right-hand side. Okay, so whenever you have solids that have transition metals in them, you have to worry about two possible competing reactions. Okay, there's solubility, but there's also formation of complex ions, and they sometimes go in opposite directions.